Hello teacher! In today's video, we are going to build and explain a 555 timer-based relay control circuit. This circuit takes 12-volt DC power source and uses it to control a 212-volt AC load, in this case a light bulb. You see exactly how each component works, why it is there and how they all connect together. In modern electrical and electronic engineering, controlling high-power appliances using safe, low-voltage control system is a fundamental requirement. This project showcases the design, simulation, and implementation of automated time-delay relay control circuit built around a versatile timer IC configured in monostable multi-vibrator mode. The system acts as an intelligent intermediate bridge between a low-voltage DC control network and a high-voltage AC utility grid. By utilizing a tactical combination of semiconductor devices and electromechanical switching elements, this circuit enables a user to trigger a high-voltage AC load for precise, predetermined duration using a simple touch-safe manual interface. Comprehensive project objectives. The primary objective of this project deployment are to implement monostable logic, to successfully configure and stabilize the NE555 timer integrated circuit to operate reliably in its monostable state, resisting external electromagnetic interference, to achieve high voltage interfacing, to demonstrate how low current semiconductor outputs can efficiently drive high current inductive loads without degrading the components over the time, to optimize energy management, to establish a fundamental framework for smart home and industrial automatic models where runtime limits prevent power grid strain and device overheating, to verify design via CAD simulation, to utilize Proteus VCM software to validate the theoretical timing equation, circuit routing, transistor behavior of components before moving to physical hardware prototyping. Step 1. The DC power rails and input stability network. Connection. On far left, we connect B1 to the established our power infrastructure, creating 12-volt top rail and common ground bottom rail. Logic. Moving right, we connect R1 and R2 in a series across the rails. The midpoint junction creates a stable 6-volt reference wire directed to pin 2 and pin 6 of the IC. This acts as a voltage divider and clamps the inputs to prevent fast triggering from electrical noise. Step 2. Configuring the 555 timer infrastructure. Connection. We place the U1 in the center. Pin 1 goes directly to the ground while pin 8 connects to the 12-volt rail. Logic. Pin 4 is hardwired directly to the 12-volt alongside pin 8. Holding pin 4 permanently high ensure the timer stays active and completely avoid accidental resets caused by external electromagnetic interference. Step 3. Integrating the RC timing network and trigger button. Connection. Further right, we build the timing engine. We connect R3 to the 12-volt and wire in a series with positive terminal of C1. Grounded the negative terminal. Logic. The junction between R3 and C1 is connected one side of the push button, while the other side links back to pin 2 and 6. When pressed, the button disrupts the input voltage divider, triggering the 555 timer to start charging the RC network and launch the timed cycle. Step 4. Output branching, diagnosis and protection. Connection. From pin 3, the circuit splits into two parallel control branches. Diagnostic line. Current flows through current limiting resistor R2, R4 to illuminate the red LED, giving immediate visual feedback that timer is active. Protection line. The D1 is placed in a reverse bias position across the relay coil. This critical safety feature the instantly clamps and absorbs high voltage inductance spikes generated when they are shut off, protecting the internal transistor of 555 IC. Step 5. Connecting the relay intermediate bridge. Connection. The electromagnetic coil of relay 1 is wired directly across the protection diode D1, running from the pin 3 output rail down ground. Logic. When pin 3 switches to high voltage, the current energizes the internal coil. The resulting magnetic field physically pulls the relay's internal isolated armature switch closed, creating a safe electromechanical bridge for high voltage side. Step 6. Wiring the isolated high voltage AC load bridge. Connection. On far right, we built the completely independent AC utility loop. One terminal for the V1 connects the common pivot of the relay switch. The normally open the relay connects the L1 and the lamp's return line goes back to AC neutral. Logic. When the relay closes, the isolated 212-volt AC path completes, safely lighting up the lamp for the exact duration for RC time constant without any direct electrical contact with the 200-volt DC logic side. Real-world application and industrial scope. The versatility of this time delay architecture allows it to be integrated into numerous real-world automation ecosystems, ranging from domestic convenience to industrial safety systems, smart home and building automation. Widely deployed as staircase or corridor lighting timers, when pressing a wall button keeps the lights active just long enough for a person to transit between floors, eliminating idle energy drain. Industrial process control. Utilize in ventilation and exhaust system that the fans must remain operational for a specific cooling or air purification cycle that primary machinery has been deactivated. Safety delay lines integrated into production machinery as a pre-start warning system, triggering an audible alarm or visual inductor for a few seconds before heavy mechanical components begin to move. Surge protection system use the delayed recognition of sensitive household appliances immediately after a power outage, allowing the grid to violate the stabilizer first. To bring everything to a close, I want to emphasize that this circuit is more than just a combination of resistors and timers. It represents a fundamental engineering philosophy, solving complex, high-voltage automatic challenges using elegant, cost-efficient, and most importantly, safe, low-voltage logic. By mastering the monostable configuration of 555 timer, achieving the perfect galvanic isolation via the relay, and implementing critical flyback protection, we create a system that actively saves energy and protects human life. This architecture is a fundamental stepping stone modern smart grids, industrial automation, and home intelligence systems. If you made it this far, you now understand how 555 timer can safely switch a 212-volt load using nothing but a low-voltage DC. That's a wrap on today's circuit breakdown. From a simple 12-volt battery to controlling 212 low light bulb, all through one tiny IC and a handful of components. Once you understand the 555 timer, a whole world of automation opens up for you. Keep building, keep learning, test it, and make it your own.